Hello, everyone. Welcome to today's webinar titled Solving Complex Feeder Protection Challenges and Reducing Wildfire Risk with Remote Measurements. Today's webinar is sponsored by Synaptic. I'm Teresa Hansen. I'm the Vice President of Content for T&D World. Before I hand off to our moderator and our speakers today, I need to go over just a few housekeeping items with you to explain to you how you can participate in today's presentation. First of all, if you have any technical difficulties at all during today's session, please use the question window to let us know, and our technical experts will help you out. We recommend that you disable any pop-up blocking software or extensions in your browsers because these can sometimes cause issues with a webinar player. In addition, we want you to participate in today's webinar by submitting your questions during today's events. Our presenters might be able to incorporate some of your questions into their PowerPoint presentation and discussion, but if not, they will answer audience questions after they complete the PowerPoint presentations. But you don't have to wait until then to ask your questions. You can type them in at any time, and I recommend that you type them in whenever they pop into your head. That way we'll be sure and capture those and have those when we get ready for our discussion. To ask a question, all you have to do is type it into the question window on the side of your screen and hit the submit button. Also, I want to make you aware that today's webinar is being recorded and will be available on the T&D World website within the next 24 to 48 hours. You'll be notified by an email that will contain a link to this webinar, and you can go in and use that link to go back and watch all or part of the webinar, or better yet, you can share that link with your peers and your coworkers who maybe were not able to attend today but you think would benefit from this webinar. The webinar will be on the T&D World website for several months, and it's free. So please do share that link. And finally, I want to let you know there's a PDF of today's presentation that's under the resource tab, and you're welcome to download that. So you should be able to see that resource tab on your screen right now. That's it for housekeeping. So without further delay, I want to introduce you to today's moderator, Saul Matthews. He's the head of commercial development at Synaptic. And Saul has lived in several countries while working across the semiconductor, mass storage, telecoms, mobile, and Mac markets. He has led mass adoption of technologies such as solid-state drives, Bluetooth, and Skype. Saul is driving new technology adoption with Synaptic, providing distributed sensor systems to power utilities to reduce cost and increase reliability for providers and consumers of electrical power. Saul, we'll introduce you to today's panelist, and he will be moderating today's discussion as well as the Q&A portion. So with that, Saul, I want to welcome you here. It's great to have you, and I'll turn the program over to you.
Hey, thank you very much. And hello, everybody. Greetings from honestly, genuinely sunny Glasgow, which makes a change. I've been in Scotland, normally we're in the rain. And we're going to take you through this webinar presentation with several expert speakers contributing here. So as was already presented, my name is Saul and I look after everything commercial at Synaptic. And we're going to take you through the lead title that we put out in the presentation emails talking about the challenge of wildfire prevention. And in order to explain how we do that, we're going to be looking at the underlying platform technology that we developed at Synaptic, which is about passive and distributed electrical sensing. We're going to explain the solution architecture and also give you some examples of how this is applied in the field, because there are several different ways to use this technology to solve a lot of challenges in the management of power systems, not only wildfire prevention. So there may be some other interesting information that you'll glean from the end of this, and we'll try and leave some time at the end for Q&A, of course. So your speakers today, as you can see, I'm surrounded by and completely outgunned by a lot of doctors and professors here who are experts in the field. You'll hear from Dr. Neil Gordon, who's our head of sensor technologies, about how the sensor technology works and how the platform actually operates. Dr. Stephen Blair, who is an expert in power systems management, will be talking to you about how this applies and is used in the field. I think many of you on the call will probably know by reputation Bogdan Kashteni from Schweitzer, who's here as a strategic advisor for us to talk about some of the specific challenges that we will encounter with the management of remote and distributed networks and what happens to these remote spans that can suffer from all kinds of problems and where we get failures at a distance away from the substation. And we'll also hear initially from, when I hand over, from Professor Campbell Booth, who is the Vice Dean of Strathclyde University here in Glasgow, and is a sort of global expert consultant to many power utilities about the challenges of integrating renewables and operating highly complex high voltage power systems around the world, and all the challenges for protection and control and the stability of networks that infers. So hopefully you'll find something interesting from all of them, with Campbell leading us off. And before we go to that, we ought to explain for some of you who we are. So you might not be familiar with Synaptech, but actually that's maybe only new news to you. We've been around for nearly 10 years now, based out of Glasgow in Scotland, with operations across Europe and now in North America, in the Gulf states, and also Southeast Asia and India. And fundamentally, Synaptech is about distributed electrical sensing, or said another way, distributed sensors. We invented a way, and we still develop and manufacture here in Glasgow, completely passive sensors which are able to measure critical parameters like voltage or current far outside of the substation fence, because they're totally passive. These sensors require no power supplies and control power. They don't require copper wiring. They don't require any kind of internet connection or 4G network. They're only connected through optical fiber and light to bring real-time visibility and control for remote or inaccessible assets back to the center. And this is good enough for transmission-grade protection applications, and also remote condition monitoring of critical assets. So you can see some examples of the customers here, and I won't try to précis this or prejudice the presentation, because I'm going to hand off now to the team, and Neil and Stephen will be taking you through some relevant examples. But the single concept we want to start off with this presentation with is that this might be a new technology to you if you haven't heard us before, but it's not new to the industry or to the market. And we've got applications and deployments of this technology in quite a few different high and medium voltage power networks around the world, which we'll share with you in a moment. So with that, and having set the scene about what Synaptech is and does, we wanted to hand off now to Campbell, who's going to take you through the next slides, which are talking about the challenges specifically of managing and protecting these complex feeders over wide areas. Campbell.
Thank you very much, Saul. So as Saul mentioned, I am one of the founders of Synaptech, but I remain in academia. So my main day job is leading the Faculty of Engineering here at the University of Strathclyde in Glasgow in Scotland as the Vice Dean for research. And I also continue to work on several research projects, very much focused on future electrical power system challenges, centred around the challenges associated with decarbonising our energy system, the electrification of heat and transport, the massive penetration of renewable energy resources, and of course the role of other energy vectors such as hydrogen, heat, gas, even water, and ensuring the flexibility and resilience of the system, and really trying to figure out what many of these changes that are happening now will mean for the future. There will be certainly many challenges that we must overcome to ensure that our future clean, multi-vector energy system retains the levels of security and reliability that we all enjoy today. I mentioned trying to figure out what this all means. Well, I think one thing that we can say with certainty is that it definitely means that electricity is going to be even more important in the future, and that the distribution system, which we're going to talk about today, will be subject to truly massive changes that we have never seen before. They're already happening. We've got new loads, new magnitudes of loads, new types of loads, new generation connecting at the distribution system, which was previously passive in nature, new interfaces, new different types of energy that are interfacing to our distribution system, different flows and different behaviours. And what this also means is that we will need more applications to monitor, control and protect our electricity network, and more measurement data to enable these applications. And this may increasingly include non-electrical data. The application that we are talking about today and that you're going to hear about today is only one of the applications that is facilitated by the distributed measurement solution that Synaptech provides. We will talk a little towards the end about the more general benefits and wider applications, so please do keep this in mind. So thanks very much, and I will now hand over to Bogdan to take us through the next part of the presentation. Thank you.
Thank you, Campbell. Let's talk or start with power line caused wildfires. This is a hot topic recently, no pun intended. We simply see more fuel available to wildfires because of droughts. Also, there is a reforestation happening because the agriculture is increasing its efficiency. We reclaim some land from agriculture that becomes forest typically. Human beings like nature. They like living close to nature. So we have effectively loads moving close to forests and areas that may be prone to wildfire. Distribution circuits are protected with time overcurrent type of protection. That means that we have a slow fault clearing time. And as a result of that, we have large energy released at the fault point. Tree contacts may last for a very long time before they are tripped. This is because the little twigs and branches, they need to dry out first. They need to develop a carbonized path in order to draw enough high current to activate the time overcurrent protective relays in a substation. As a result of that, we shouldn't expect high sensitivity to high impedance faults or to down conductors. We all know that there is the feeder relays with specialized built-in protective functions that claim high impedance fault detection and down conductor detection. Those technologies are out there for about 20 years. There is a lot of field experience, and that field experience is not extremely positive. Those technologies do work, but they don't meet the expected requirements to really address the wildfire and public safety issue. When it comes to mitigation is expensive. So obviously you start with rigorous right-of-way vegetation management. Ideally, you would like to use the right-of-way as a fire break. That means that you may clear vegetation all the way to mineral soil or even applying gravel. Undergrounding overhead feeders is contemplated. This is not only expensive, it would also take a very long time to convert all our feeders into cable circuits. The isolated overhead conductors is something in between, so you retain the infrastructure of the poles and the right-of-way the way it is, but you cover the conductors with a dielectric. There is some new technologies out there. So one of them is to use the ungrounded compensated networks. When you use the Petersen coil to squelch the capacitive fault current, and then add on top of it a power electronic based injection in order to counter the active component of the fault current. As a result, the idea is that you will reduce the fault current to below maybe 1 ampere primary, and that is claimed to be low enough to prevent ignition. That idea is out there, but it's very expensive. The numbers I heard are to the tune of $8 to $10 million per distribution substation. There is some other experimental technologies, such as using touchless traveling wave measurements and using timestamps of traveling waves to provide better protection of distribution feeders. I would like you to keep that slide in mind, because this is our reference point for any other better technology to address wildfires and other issues. None of the solutions that we are looking at today is fast, none of it is cheap, none of it is simple. Now, when you look at distribution feeders, wildfires is not the only challenge. They become more complex with complex topologies with multiple sections and branches. For better availability of power, we tend to use looped circuits with ties closed. So we have a bidirectional short circuit current flow. We have reclosers in order to separate the feeder and provide more selective tripping. Loads are increasing. There is distributed energy resources added, and they are not synchronous generators, as you know. They are typically solar, and they are power electronics based, so they have an unusual fault current response. That leads to the issue of microgrids, either preventing microgrids from forming or protecting and monitoring them. And then this micro power system that we keep calling a feeder it has all the other features of a energy distribution apparatus. So you will have pole-mounted capacitors in order to maintain voltage profile and provide power factor compensation. You may have automatic voltage regulators. So for all economical reasons, we have this complicated structure that we refer to as just a distribution feeder, and we try to protect it with time over current protection. So traditional protection may not be adequate. Obviously, the time over current coordination times stack up, and that means that we have a slower fault tripping time when the fault moves closer to a source, exactly the opposite of what we want. Then the power quality expectations are increasing because the loads are becoming more fragile. The distributed energy resources, they challenge time coordination, and they also challenge directional elements if you need them at recloser locations. Faulted section identification is very difficult unless you use the faulted circuit indicators, or as some of you may know them, fault passage indicators. And when using measurements at the substation, for locating is nearly impossible. And I would argue down conductor and high impedance fault detection is nearly impossible. Those relays, feeder relays located at substations, they kind of fight the fight with one hand tied behind their back. So our thesis is that we cannot trust the high impedance and down conductor relaying methods at the substations. They're not sensitive enough and they're not fast enough. Those of you who tried those relays, you know that they may take tens of seconds and longer to detect a high impedance fault or down conductor. From our experience in transmission systems, we know that multi-zone differential protection can deliver the required level of protection. And I will explain what multi-zone means. So our thesis is that you could significantly reduce the wildfire risk or reduce it enough by practicing better protection and by practicing hygiene. So better protection is differential, and you will be able to trip instantaneously for faults anywhere along the feeder, trip before a down conductor hits the ground, or at least have a significant chance of doing that, and also trip instantaneously for tree contact faults or other high impedance faults. Better hygiene means that you keep the feeder in a good shape. So, for example, things like you will eliminate the risk of mid-span phase faults due to galloping conductors by reducing spacers. Those faults are really difficult to detect because before the time over current element times out, the fault is kind of gone, but it created energy that may result in a wildfire. And then, of course, managing vegetation to appropriate high standards. So a differential protection is a proven solution. So assume for a second that you are able to put current transformers at key points along the complex feeder. Those current transformers provide signals to substations, and those signals are real-time, high-fidelity signals. It is as if you had long wires, secondary cables that deliver that signal all the way to the substation. You know that you could do a much better job protecting that feeder. Differential protection is extremely fast, so you will have a sub-cycled fault detection time for all faults, regardless of their location. Differential protection is extremely sensitive, so now we are going to trip high impedance faults such as tree contacts. And because you have those CTs throughout the feeder, you could provide a better down conductor detection because you are closer to the problem, so to speak. So it's a wealth of opportunities. There is nothing really new on this slide. The bullets summarize the key advantages of differential protection. Differential protection is practiced for many decades, close to a century, in transmission networks. We are all very familiar with this powerful principle. So the figure on top shows that I divided my feeder into small differential zones when each section either of the main trunk or the laterals is protected with individual 2-terminal differential zone. The figure at the bottom shows that I may choose to protect the main trunk with a larger zone and then each lateral with its own differential zone. So my fault detection is becoming much more granular and also sensitive. My tripping zone, of course, is limited by the current interrupting devices that I have there. So regardless which zone detects a fault, I am still going to trip the CB1 at the substation and recloser 1 somewhere along the feeder, and I may send direct transfer trip signals to the DER if located or connected to that tripping zone. Small differential zones give me better sensitivity, better speed, better selectivity. The CTs allow me to detect down conductors. Differential protection is dependable despite the DERs and their unusual fault response. They have very simple settings. I would argue that you could run them with default settings. I would have a better way to provide backup. So even if I use time over current as a backup, I have CTs now located closer to the fault, so my coordination times are not going to stack up that high and I could trip faster. I have CTs in front of my loads and DERs, so I could provide better backup for faults within loads and DERs. Now I have voltages from both ends of a faulted section, and I could also get the voltage. So now I am able to run impedance-based fault locating. And because I have visibility inside that feeder, I could allow microgrid, I could monitor it or even protect a microgrid. So again, nothing new. We know that this stuff is very powerful and it solves a whole range of problems, not only wildfires. So if this is so simple, why aren't we using this? Well, we kind of self-censor ourselves. A micro substation on a pole is a non-starter. If I were to put IEDs to measure the current, then I will have to put a dependable communications channel to communicate those currents. And I would argue that wireless is not going to work for protection applications such as differential. I will need control power to run those IEDs, both relays and the communications gear. I will have to have housing to host the equipment in a weatherproof fashion. I will need crew access for maintenance and testing. And by the way, that crew access should be something a little bit better than that orange ladder that you see leaning against the pole. Then I will have to provide cyber and physical security. So long story short, a solution exists. If you are practicing protection as it's practiced in transmission grids, you know how to protect a feeder. It is just that solution is just dismissed because of the cost and complexity reasons. And if you need to understand that, just look inside the control cabinet for a typical recloser. You will have some kind of a relay there. You will have a battery to provide backup control power. You will have to have a rectifier or charger to maintain that battery, some kind of radio or wireless access for controls, and so on. So before you know it, you do have a micro substation on a pole, and that's not very attractive. This, however, is changing, and there are two key enablers that allow us now to dare think about differential protection and all the other protection techniques from transmission systems in applications to distribution. So the first one is the old dielectric self-supporting fiber. Those cables are relatively inexpensive. They are easy to install. You could install them without taking an outage. And many utilities already use those cables, whether they lease them to local telecommunications companies or use for their own reasons. The current measurements that we want to see need to fulfill the following requirements. I would like to have remote measurements, meaning traditional CTs are interrogated via fiber. Interrogated meaning accessed. The system needs to be passive, meaning no active electronics or control power outside of the substation fence. Weatherproof, I don't want to be building any housing for that equipment. Distributed, meaning that I could access many cities through the same fiber. Time coherent, so all the current signals are aligned and I don't need any time synchronization solution either outside of the substation fence or inside. And finally, interoperable, meaning that when those signals are given to me in a substation, I want them in a format that could be understood by many other devices. So practically, we are talking about IEC 6150 sampled values. So our thesis is that we do have these two enablers, and now we could redefine the game in distribution protection. So the next step is to see how this is even possible. I'm going to hand it over to Neil Gordon, who will share more details about the distributed passive electrical sensing technology. Neil?
Thanks, Bogdan. So as Bogdan said, I'm just going to take us through a brief introduction to this passive sensing technology and how that enables this multi-zone differential protection solution that Bogdan has just described. And we refer to this technology as distributed electrical sensing. So this technology allows us to deploy passive point sensors for electrical and mechanical quantities distributed in series over standard single-mode optical fiber like ADSS. This means that we can deploy any combination of electrical and mechanical sensors. So that means sensors for current and voltage, as well as strain, temperature, vibration, and overhead line sag, using existing single-mode fibers, standard telecoms fiber. Each system consists of a central powered interrogator system and a string of sensors which are wavelength multiplexed over single-mode fiber. Now, all of those sensors operate in reflection. So that interrogator, as you can see here, it illuminates all the sensors in the array with a broadband light source, and the measured quantity from each sensor is encoded in the wavelength signal that's reflected back from each sensor. Now, because the measurements are multiplexed and encoded in optical wavelength, they're very robust to electrical interference, EMI, or fiber disturbance along the fiber run, and they can reach out very long distances because of that. Now, electrical sensing is our focus today, and the electrical sensors are connected to the secondaries of industry standard current and voltage transformers to passively convert the AC electrical quantity into a wavelength modulation. And that's what's kind of measured locally at the interrogator. So those measurements are centralized and served by that interrogator, and the interrogator can sample all of the connected sensors simultaneously at up to 288 samples per cycle, and it can output the full IEC 61850 sampled value waveform and perform decisions with embedded protection and control functions as well. So this method combines established fiber technologies with trusted standard instrument transformers like current and voltage transformers, allowing current and voltage measurements to be deployed over long distances outside the substation fence and with no supporting infrastructure besides that telecoms fiber. So in terms of the system architecture, each single interrogator can support up to 30 single-phase measurements or up to 10 three-phase locations on one single-mode fiber. And without using any additional amplification, the maximum sensor distance is about 60 kilometers or around 40 miles from that central interrogator. And with amplification, we can stretch that further. Each interrogator can output IEC 61850 sampled values directly to the process bus, and it can accept standard time synchronization formats like PTP and PPS. And it can also output in traditional dry contact format for traditional systems. Now, importantly, because all these measurements are centrally time-stamped by the interrogator, that means that every single sensor deployed down that fiber will maintain relative time sync, even in the absence of GPS signal. So that means that any measurement any protection functions rather that are deployed on that system will continue to operate even if GPS is interrupted or lost. And multiple interrogators can be coupled via PPS so that you don't lose relative time sync in your entire system, even in the event of loss of GPS. And here you can see just a couple of images of the medium voltage electrical sensors. So you have the photonic current and the photonic voltage transducers. As you can see, these are a very familiar form factor to standard devices in the sector because they are simply optically instrumented standard CTs and VTs, and they maintain safe dielectric fiber optic output. Because these require no copper or digital telecoms or time sync at the measurement location, their footprint and their installation times are kept very low, so there's minimum disruption from the installation. And on the next couple of slides, I'll just take you through some specifications for each of these devices. So here you can see what the interrogator looks like in practice. So this is a 3U rack mountable device capable of sampling at up to 14.4 kilohertz as standard. It's compatible with IEC 61850-9-2 and Goose outputs as well. And importantly for a device like this, it is type tested to the same standards as protection relays for substation environments. So that means IEC 60255 and 60068. And just moving on to the sensors as well. So here you can see some of the specifications of the PCT and the PVT, the current and voltage transformer. Both of these can address all standard transmission and distribution current and voltage levels by selection of the appropriate primary transducer. The image on the right shows some 33 kV combined current and voltage sensors, which have recently been manufactured and are under test. And again, both of these employ standard single mode telecoms fiber. So this, along with the use of standard CTs and BTs, is why the devices are so straightforward to install. So installation can be performed without any specialist skills beyond those that already exist in the sector. And that's basically mounting of the instrument transformer and standard telecoms fiber splicing. So there's nothing terribly unfamiliar to installers in the sector, which is what makes these so straightforward to put in place. So that's a very, very quick overview of how the technology works. And I'll just pass over to my colleague, Stephen Blair, now to discuss the solution architecture.
Thanks very much, Neil. So you're probably thinking that an obvious drawback with this remote sensing approach is that it needs fiber to operate correctly, which may not already be deployed, especially in distribution systems. But as Bogdan already explained earlier, there is a relatively cheap and practical fiber deployment solution already available, and that's using the ADSS approach. And that's much cheaper than the alternatives, such as using an optical ground wire. And also many utilities will already have experience in deploying ADSS fiber. So the way that we would suggest deploying this is that the fiber can effectively loop around all of the essential points on the feeder or the circuit, such as recloser locations, any teed lines, and DER connection points. And then sensors can be readily deployed at these locations as required. So typically that will be CTs for protection, but it could be VTs and other types of sensors too. And another benefit is the operators can also use the same fiber for other applications too. I mean, typically ADSS fiber will have multiple bundles there available. So there'll be lots of fibers that can be used, and other features can be enabled, such as operating reclosers, transferring intertrips, and it can even be leased for other services. So with that fiber infrastructure in place, sensors can be readily deployed wherever it's useful, really. And the synaptic approach, which Neil has explained, can be used to connect to existing CTs. So we can connect to the secondary of existing sensors that are already deployed, pole mounted or otherwise. But if they don't exist, we can also readily supply CTs can be fitted, and that can be connected to the fiber also. And by selectively adding voltage sensing at some strategic locations, you can get distribution fault location capability with quite good accuracy, which we'd expect to be around about 5%. That basically immediately becomes possible through this approach. And this is sort of the holy grail of distribution protection, being able to pinpoint where faults occurred with high confidence, even with complexity of DERs and other things going on in the circuit. So as Neil's already given you a flavor of, the synaptic interrogators can perform differential protection on board, and that can be done from multiple zones in real time on the device itself. And as you'd expect for differential protection, this provides sub-cycle operation for faults. And some of the things that Bogdan's already hinted about, we can add some extra provisions here relatively easily to help countering wildfire-specific events. So high impedance fault detection and open circuit protection, they can play a part here in helping with wildfire prevention. And that becomes significantly easier compared to just making decisions based on substation measurements, where you're restricted to what you can see. This approach can also help to optimize autoreclose on circuits which have a mixture of conductor types. So obviously you want to block reclosing for cable faults or in scenarios where there's maybe a high risk of wildfire. So having that capability to discriminate between cables and overhead lines can be very useful. And in general, the solution is kind of building towards a centralized feeder protection platform where all of the remote measurements are available back at the substation, and good decisions can be made to protect every aspect of that feeder. The solution is also very scalable and flexible. So a simple deployment could actually start with just one key zone. Even adding a few remote CTs can provide a pretty good payoff by greatly improving the protection speed and sensitivity. Then that can expand over time to add more functionality and provide more granular fault detection zones, as Bogdan explained earlier. And some of the critical functions can be implemented on board the interrogator device. It's a real-time platform which is designed for that purpose. But also all of the measurement data can be delivered to other devices in standard formats. So this can be integrated into wider solutions if needed. So the idea here is we're trying to make it as flexible as possible and future-proof. And as Neil explained already, multiple interrogators can work together with coherent time sync of measurements to further expand the coverage for particularly complex circuits with DER, T-blinds, and other things going on that add to the complexity. So next, I'd like to give everyone a bit of a flavor of some of our typical deployments. This slide summarizes some of our deployments so far, and these span across many different applications, including high voltage grids and offshore wind, where there's good opportunities for where having remote and passive measurements becomes very useful. But I'll focus on just a few of these that are especially relevant to today's topic. So here in Scotland, we've deployed a system which performs a single-ended differential protection on a 132 kV circuit. So a single fiber is able to collect remote CT measurements, local and remote measurements, in this case over about 50 kilometers. And then these are brought back to a central location to perform the protection function. And all of these measurements, even from 50 kilometers away, are available centrally in less than 1 millisecond. Typically it's faster than that, but 1 millisecond is usually the limit. So in this case, this approach allowed new teed connections, which are typically going to be from large wind farms being connected into the grid, to be very cost effectively protected. Otherwise, a lot more infrastructure would be required to support relays and provide auxiliary backup supplies and everything else that would be needed. This also, importantly, avoids some of the compromises of distance protection, where it can be very difficult to set the settings and then prove that they are correct for all possible scenarios, whereas this relies just on the kind of tried and tested approach of differential protection. And here on the slide, you can see some photos of that installation where we have some sensor units which are installed in kiosks in the substation, and they connect to the secondary of existing CTs. Or as I mentioned earlier, we can connect to brand new CTs if that's needed also. And in this case, the interrogator was providing streaming sample value data to various IEDs in the substation. So we've installed what I think is a very interesting system, which is monitoring the health of a very important 400 kV cable, which happens to be under Madrid Airport in Spain. And cables such as this span, many miles. In this case, it's in a tunnel, but it could be in a duct or some other approach. And these are very difficult difficult and time-consuming, and I guess quite unpleasant to have to inspect these cables manually because of the distance involved. But at the moment, that's really the only solution, is that people need to walk the distance of the cable and inspect the terminations and joints. And we know that those cable terminations and joints are often the source of failures. So the sensor system that we've deployed is it's monitoring phase currents, sheath currents, and the joint temperatures. And that's distributed along the length of the whole cable. So this is a very good fit for passive sensing, where we can install the sensors once, but for the lifetime of the system, we get streaming measurements from all those locations. And what we're working on at the moment is using the sensor data to find early warning signs of any degradation of the joints and terminations to give advance warning to the operator of the health of those assets kind of degrading. And here there's just a couple of pictures where you can see some of the fiber routing to the wall-mounted sensor units, which was during the installation last year. So the final application I want to mention here is, and this is another example of where this technology is very well suited, and that's for protection of mixed or hybrid circuits, which have sections of both cable and overhead line conductors. So clearly it's beneficial to reclose for overhead line faults, for helping with overall security of supply, but it's also crucial to block auto reclose for cable faults. And conventionally, this is a difficult problem to deal with for utilities because installing remote measurements is expensive. So for this deployment, we installed a system in India, which had remote CTs at the transition point, and that essentially provides perfect discrimination of the faulted section. So the system will provide a clear signal to either block or allow auto reclose for all foreseeable fault types and positions. So in this particular deployment, even though these cables are relatively short sections going from the substation to the transition point, this will carry some risk around cable faults not being dealt with correctly, but this solution eliminates that scenario entirely. So, and also in general, this solution, it scales up well for more complex scenarios where there's multiple conductors, perhaps parallel conductors, and also if there's multiple transitions over a significant distance. And so finally here, there's just a few pictures of that installation where you can see some of their CTs, which are coupled to a fiber, and then all of the measurements are brought back to a central location in the substation. So now I'll hand back to Campbell, who will kind of round off some of the overall benefits of this approach.
Thank you very much, Stephen. So I think what I'm going to say is a repetition of some of the points that my colleagues have made earlier. And there have also been quite a lot of questions coming in, which we're trying to answer online, but it's great to see the level of interest and engagement. So what we're talking here are some of the more widespread benefits. Some of them apply both at distribution and transmission at all levels, but really using these distributed measurements as we've shown here, it does throw open opportunities to do this kind of distributed, scalable differential protection with a greater or lesser amount of granularity. It also allows you to do other things just based on perhaps comparing currents and seeing how currents are dropping off, perhaps even doing directional comparisons as opposed to just magnitude and/or magnitude and phase. It can be made to be very sensitive, which is the whole point of this detecting down conductors very quickly, almost as it's happening, to avoid this or reduce the risk of these wildfires being initiated. The impact of distributed energy resources on traditional passive distribution networks or previously passive networks can have effects on fault levels, which can then affect traditional overcurrent protection. But if we move away from that overcurrent protection, then it means that if we have differential, we can be more sensitive, more discriminative, and of course we can be faster, which in the fourth point in this slide is shown through, we can reduce the amount of energy that's actually released during the fault. And we can trip for all types of transient faults, temporary flashovers, things that might be caused by conductors clashing together. These can all be detected and cleared if required very quickly. If you have measurements from a lot of places, then that opens up opportunities to be a bit more sophisticated about your backup protection rather than maybe just using time and current graded systems. If you have this differential type of measurement and distributed measurements in general, you can apply some logic and algorithms to actually identify perhaps when a breaker has failed and trip those adjacent breakers more quickly using like a kind of circuit breaker fail type logic that you might find in a transmission substation across a network in a distribution system. And faster clearance may be good if you've got more sensitive loads and of course more distributed energy resources in our future systems. And talking about the future, some networks may be permitted to operate in islands or may not, so we can use our distributed measurements to detect those islanded or non-islanded conditions or grid-connected conditions. And we can do all sorts of sophisticated monitoring and facilitating things like distributed energy resource right through, also looking at things like asset integrity, looking for hotspots, looking for power quality type phenomena as well. All of this is enabled by this general platform. Again, speaking about some of the operational benefits, we could, if we can identify the faulted sections, then we can do more sophisticated and more selective autoreclosing or restoration functions. We can locate the faults. If you have voltage measurements at some locations in the network and you have a good knowledge of the impedance between those voltage measurement points and the distributed current measurement points, then you can start to think about sophisticated voltage estimation type functions, which could be used either to detect faults approximately within feeders and to the exact location, and it could also be used to detect potential voltage problems, either excursions from voltage dips or over voltages, for example, if you have a lot of generation connected to a feeder. Of course, reducing losses and of course reducing the unwanted losses that are sometimes caused by theft of energy, that can again be enabled by this sort of multi-zone differential protection and knowledge of what's happening at more locations in the network rather than just at a very small number of locations. And I think in general, our platform enables this kind of higher granularity of measurement, and you can think about this kind of feeder local area network or maybe Internet of Things, where our distributed generators and the various measurement points can be used to try to really figure out what's going on out on the network to enable lots of applications. So I think that's really all from me, and I'm just going to hand back to Sol to complete the webinar. Thanks very much.
Thank you, Campbell. And in fact, thank you to all the team. So Bogdan, thanks. Also Stephen and Neil for taking us through this. We've been rather running out of time in the background here to answer questions live. There have been so many, but that's a good sign because, of course, it's a new concept and a new technology. And we could spend a lot of time here talking to you about how we work and how this reduces the capital cost of instrumenting a network or the operational cost savings that come from being able to automate remote monitoring of, assets which are far away or simply difficult to reach. And of course, all this is about enabling better resiliency, better protection and control, increased security and indeed safety in these power systems. So there's potentially a lot to cover here, but we wanted to leave the last 10 minutes to try and capture some Q&As. And I think one of the things that keeps coming up, and I'll just take one of them now, we might run out of time, but looking at all the questions coming in, I can see the same one coming over and over. So Neil, can I throw you under the bus and ask you to join back in here? Because one of the key questions was, okay, can you re-explain the sensor technique? So how we go from, say, a current or a voltage to the strain to the light measurement, and what are the environmental considerations? So, how do we regulate for environmental and ambient temperature effects? How do we deal with environmental factors like EMI? That would be pretty useful for everyone to understand the robustness.
Sure, I'll try and be brief. So the core technology is really the conversion of the secondary quantity, so the secondary current or the secondary voltage out of a standard CT or a VT into an optical wavelength signal in the fiber. And that's quite different to other optical NCIT kind of Faraday effect like sensors you might have come across before, which encode the measurement in the polarization of light. Now, in the case of those sensors, the polarization can be affected by electromagnetic interference, and the materials of the optical sensor will obviously respond to temperature at the local location, requiring an independent temperature measurement often in order to compensate those measurements. So the way our technology is different is we don't encode in polarization, we encode in wavelength, which is incredibly difficult to change once you've encoded that measurement over long distance through temperature changes of the fiber and through electromagnetic interference. You don't change the wavelength. So it's incredibly robust once you have converted that secondary current or secondary voltage into wavelength. It's very difficult to change that into to interrupt it or to change it. And then at the sensor, of course, our sensor is made of materials, and those materials will change with temperature, so that there is a temperature influence on our measurement. But one of the unique things about our sensor is that in that passive optical measurement we receive, we also have, for free almost, a measure of the local temperature of that sensor, kind of encoded in the same signal. And that means that we can perform an active correction for any temperature effects of the sensor that happen at its location. So we know instantly if the temperature has changed of that sensor, and we have calibrated it in our facilities to correct for that value. So every sensor you put out there will respond to temperature, but we have this benefit that without having a separate powered temperature measurement at that location, we know what the temperature is and we can actively correct for it. So hopefully that answers your question.
Yes, appreciate that. Thank you. Now, I think one of the other ones that keeps coming up here then is also to understand not necessarily the actual sensor technique, but the fact that we can mix and match these mechanical and electrical measurements in the same system, even through the same fiber. People were talking about, how do we interleave these things, and how do we actually measure things like a temperature versus a phase current in the termination of a cable or a link box, I think was probably what was driving it. So could you briefly also try to explain to everyone how it is that we can do mechanical measurements all in the same system, and how we then manage that, back at the interrogator level in terms of, synchronously then publishing that information together?
Sure. Well, the technology that kind of underpins what we do at Synaptic is called a fiber Bragg grating. So if you want to look that up, that's probably the easiest way to get familiar with it. But it's fundamentally it's the device that does the encoding of the measurement into that wavelength signal. And Synaptic's IP is in using that for an electrical measurement, but you can also use them for mechanical measurements as well. And as far as our interrogator is concerned, they're all identical. They're all just wavelength signals that are being delivered back to the interrogator in reflection. So the interrogator is basically agnostic as to whether the signal it's receiving is a wavelength, is a voltage or a current or a temperature or a strain or a vibration. They all look the same to the interrogator. And it's about how we calibrate those sensors at our facilities and the algorithm we deploy on the interrogator to convert each of those wavelengths into the parameter that's actually being measured at that location. That you mentioned, Saul. So that's an important thing to touch upon because we multiplex all of our sensors along a single mode fiber by wavelength, and because the speed of light in the fiber is a very well characterized, well-known quantity, that means for every sensor, and most importantly for the electrical sensors where you need those to be properly synchronized to GPS, we can kind of align those measurements sample by sample back at the interrogator, because we know the time of flight in the fiber and we can correct for that actively. So it means that you bring all those sensor measurements into global alignment back at the interrogator with GPS time without having to do any kind of clever calibration. You just need to know the distance in the fiber to do that.
Okay, and then thank you, Neil. And perhaps one other question that covers a lot of bases from the Q&A that I've seen, and maybe I'll throw this to any of the four of you experts here. So there was lots of questions around, okay, how fast do we need to respond before that line hits the ground and ignites that wildfire? You know, and how does this technology lend itself to that? So I don't know if there's a time to aim at that is a standard one, but I mean, maybe Bogdan or Campbell, you might have some thoughts on that in terms of the event versus our speed to catch it.
Yeah, let me maybe try. So, you know, there are some experimental deployments at some utilities on the west coast of the US when you know, they have some actual data. When you look at the down conductor, just because how gravity works, you will have more than a second before that conductor hits the ground. So any method that is able to detect open phase condition will have enough time to clear that, to de-energize that feeder. So when the conductor falls down, there is no real energy kind of pumped into that spot. Now, can you detect an open conductor? You could do this through a number of methods if you have measurements close to that spot. So specifically, if you have currents at both ends of the affected section of the feeder, you stand a good chance of reliably detecting open conductor. Now, if this is really a very critical wildfire situation, you may choose to overtrip just to be on the safe side. So, you know, one thing that, you know, if you really cannot afford even a small risk of wildfire, say because the fuel is really dry and maybe you have a high wind situation, you could just trip on the loss of load on that feeder, on that section of the feeder. So, and there is other ways to kind of detect an open phase condition, and the down conductor follows open phase after a second or even more. This is how long it takes for a piece of wire to actually drop to the ground. So I think this is way more promising than looking at the total current in a substation and trying to figure out that you have an open phase condition somewhere on that complex feeder.
I think maybe
Great,
also, if I could add to that as well, you mentioned the kind of the galloping conductors or the vegetation encroaching on the line as well. I mean, if you've got a traditional overcurrent that may be delayed by several hundred milliseconds, you know, even if that fault is burning across onto vegetation, which could then lead to a wildfire. So not even a downed conductor, but potentially using this type of technique, you could clear that more quickly because that requirement for that time delayed discrimination could also be removed. So that's another non-downed conductor example of where faster protection in a distribution network may help, as well as the ride through and the other stuff when we've got a far more active network in the future. Thanks.
Thank you, Campbell. Okay, everyone. I'm going to suggest now that we stop the Q&A segment because we need to be respectful of everyone's time. We're coming up to the end of our hour. So just to say thank you on behalf of our team here and our speakers for listening to us. And I hope it was useful, judging by the kind of Q&A and the amount of questions we got. It certainly was. If we didn't get to your question today, we captured it. We will get back to you and respond to you offline. And also for all of you who have been kind enough to give us your time today, we've also written a full white paper on this subject, which we will supply you in the follow-up to this webinar. So you'll get exclusive access to that and something to read on for a while. But we will respond to all of you and try and follow up with everyone's questions as we can. And our contact details indeed are one of the slides in this deck, the PDF of which is available to download here and now. So with that, we hope that that was a useful webinar for you, and we'd like to thank you, and we'd hand this back over to Teresa from T&D World, who will now close us off.
Yes, thank you, Saul, and thanks, Campbell, Bogdan, Neil, and Stephen. Also, it was a great discussion. As Saul said, I think we had tons of questions, so I know that you guys got something out of the discussion too. But before we go, I just want to thank you, audience, for taking time out of your day to be part of our webinar. We know that you're busy. We really appreciate you taking the time out. I also want to remind you that you will be receiving that email with a link to the archived webinar. So if you need to go back and look at it, you can do that. And better yet, please pass it along to those peers and coworkers that you think could benefit from it. So on behalf of TND World, I want to thank Synaptic for sponsoring today's event. And of course, I'll thank our panelists once again for that great discussion. With that, that concludes today's webinar, and have a great day, everyone.